This is Patrick O'Shaughnessy. I'm a certified industrial hygienist and a professor at the University of Iowa. And I will be discussing real-time data collection techniques in this module devoted to data capturing and organization that's associated with the InTERACCT series. In the second of 4 parts of this module, I will explain the fundamental properties of direct reading instruments in terms of the data they produce, and then provide a few examples of using a spreadsheet to best organize data obtained from those instruments. So with real-time data collection, typically the sensors can store data collected over time and then stored on a data logger. That information then has to be downloaded to your computer via software that's generic to that particular sensor. Then once it's outputted to a spreadsheet, often in text form, the data needs to be translated into numeric form, and then it can be visualized in the spreadsheet using a graphing techniques, or analysis of the information can be done statistically, as will be described in the statistical analysis module. Prior to data collection, you will want to consider the sample rate of the instrument relative to the length of the sampling period. A question you may want answered by using a direct reading instrument is how constant or how fluctuating concentrations are over time. Then, are you interested in minute by minute or second by second fluctuations? Typically in the world of aerosol concentrations, for example, we don't really need to be concerned about fluctuations on more than a minute by minute basis. And so that may be plenty enough time in terms of sample rate to get an idea of how the aerosol concentration is fluctuating over time. The other concern is the resolution of the sensor. How well can the sensor distinguish one concentration value from another? So for example, when a concentration increases, how much does it have to increase before the sensor recognizes that increase? Ultimately, resolution is a limitation of the sensor itself, and nothing can be done about it other than buy a more expensive sensor that has a higher resolution. And then a final consideration is the concentration range over which you expect to be measuring. And can the sensor take readings within that range or not? To illustrate these points, here's an example of output from a hydrogen sulfide gas sensor. Initially, concentrations were very stable and down to almost nothing for quite a while. And this data was taken in a wastewater treatment plant where the worker was moving between different areas of the plant. Concentrations started increasing in the afternoon, as you can see. So for this example, the question is not to worry about the data and what it means, but rather, is the sample rate too fast or too slow? In this case, the x-axis tells me that between each major tick of the graph is a half an hour, and there are a fair number of points between each half hour, which seems to be enough time resolution. But on the right, where there's a lot of variability over time, readings are swinging way high and then way low, so to capture the true nature of the concentrations, the sample rate may not be high enough to understand what's going on within each one of those swings. You'd like to have more points in between them. To analyze this data further, here is a short snapshot of it where we can see that over the 30-minute period there were 10 samples. Therefore, the sample rate is 3 minutes per sample, and the sensor resolution is seen in the vertical aspect of the plot. As you can see on the right, there's no vertical spacing smaller than between the two that are shown, which indicates the sensor's resolution. So the smallest jump, so to speak, between concentration measurements and therefore the hydrogen sulfide concentrations, they have to increase or decrease by at least that amount to show up as a different concentration from the previous reading. In this case, that jump is equivalent to 0.1 parts per million. Again, the question now is whether that resolution is good enough for the situation monitored. Here, as another example, is output from an aerosol photometer, which reported aerosol concentrations over time while monitoring a silica-containing particle. These concentrations are shown over an 8-hour period, or 480 minutes, and the sample rate was once every 15 seconds. So you can see it's a lot noisier, so to speak, than the previous graph showing the data values taken once every 3 minutes. The resolution of the instrument is 1 microgram per meter cubed. And you can see the concentrations are going from near zero to up about 700 or so micrograms per meter cubed, after an initial high peak that went way higher than that. Then there were some low points, say around 180 minutes, when a break was taken by the person wearing it. So these are pretty high concentrations, especially if it's silica. But again, that's not our concern right now. So what would the spreadsheet template for this look like? The related spreadsheet is dependent on the output of the software from its data logger to a text file that is then imported into Excel. And when you do that, always start at A1 up in the top left corner to be consistent between sample runs and the subsequent use of the spreadsheet as a template. The output data actually spreads out over to the H column, not the I, just the H column. You can see it initially has some information about start time, start date, etc. The first column of data gives the record number, which is the sample number, and then the actual concentration measured in micrograms per meter cubed is given in the second column, as pointed out here. From the time indications in column G, it can be seen that there is 15 seconds between each sample, which is therefore every quarter minute. So as a suggestion, it's easier to plot XY graphs with numbers that indicate the actual minutes, rather than using the text-based timestamp as your x-axis. So those running quarter minutes were added to the I column in a function, they were planted in there. Once the first spreadsheet using data from this sensor was created, it was also saved as a template for subsequent samples. In that case, the data from the raw output is again placed starting at A1, which then completely overrides the data you see here, but then the graph will be updated automatically with the new data. The only warning is to look down at the bottom of the data to see where it ends when you put new data in over on top of old data. It may not end at the same place as your template data ended, or extend beyond it, in which case more needs to be added to the time in the minutes column, and your graph may need to be extended as well in terms of the series of the graph. The next part of this module will expand on this topic of real-time data by explaining methods to distinguish trends in the data.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.